they just like need to get out of their system real quick? Cool. All right. So we're going to focus on chapter 23, right? The organometallics. One of the difficult things of this chapter is we're learning about a lot of different organometallic reactions, and they all have these like limitations on what the substrate can be. So the very first thing I want to do is to just make a cheat sheet here. So everybody make sure you have your chapter 23 lecture notes handy. You're going to use that to make this cheat sheet. And so we're going to sort of break this down into our, so like the lithium, magnesium, copper. Okay. Well, actually, I guess it's just the copper that we want. Right, so here we're going to have the limitations on R for our organometallics. And then all of these reactions involve an alkyl halide as well, and there's limitations on what that alkyl halide can be. So for the Gilman reactions, let's list those. We also have the Still, Suzuki, and then for the Heck, there's not really an organometallic for that one. We can sort of lump it into this chapter because it is catalyzed by palladium, but we still have limitations on what the alkyl halide can be. So everybody take a second and mine your notes and see if you can't make this cheat sheet about what's allowed on the organometallic half and what's allowed on the alkyl halide half for each of these four reactions. Okay, so for the Gilmans, remember we're talking about what our sort of like organometallic is going to look like is some R group attached to copper and then lithium. We have two of those, even though only one of them reacts. What are the limitations on the R group for my organometallic?
They can only be alkyl, aryl, or vinyl.
Alkyl, aryl, or vinyl. Nice. Alkyl, aryl, or vinyl. And then we can react these with halide, and those halides can have the same limitations except for even a little more limited group of alkyl. These alkyls have to be methyl, primary, or aryl, or vinyl. Okay. For the still, Chelsea, what are there going to be the limitations on my organometallic?
It's going to be aryl, allyl, benzyl, and vinyl.
Yeah, so aryl, vinyl, allyl, benzyl. Whoops. Benzyl. Okay. And then what about anybody give me the halide?
Aryl and
Vinyl and aryl.
Yep. Okay. And that's the same for the Suzuki, right? So I taught these in the same lecture because you can kind of hold these in the same place in your mind. What's the big difference between the Suzuki? There's one more thing that's allowed for the Suzuki for my R on the organometallics. Can be aryl, vinyl, allyl, benzyl, or
Alkyl.
alkyl. Okay. And real quick, what does the reagent for a still look like? What is the metal that I'm using as my organometallic? What's the metal? So the still uses tin. Whoops.
Stannin?
It's actually SN is tin, and it's called a stannin because that's the German word for tin. But yeah, I mean SN on the periodic table is actually tin. It could yeah. So I guess it's not German. It's Latin. But yeah, so that's where that symbol comes from. But yes, I mean just tin can tin. And then if it's Suzuki, what's my metal? Kind of we don't always think about it as a metal, but nonetheless.
boron.
Boron, yep. So, and then there can be a few different boron compounds. Again, I'm not going to expect you to memorize those that are popular though, that you would want to sort of have in your mind for, in case the ACS throws something at you is something that looks like this. Okay, so again, I don't expect you to have these memorized as much as I want you to be able to sight recognize them. The other one that I've seen on the ACS exam is just abbreviated as BBN. Okay, and that's this big freaking ugly, oh gosh, going back to chair structures here. Clearly been a while since I've drawn a chair. Oh my gosh, it's actually even more. It's an 8-membered ring. Anyways, it's some big, let's say big ugly ring with boron at the top. Don't need to know the structure of it again, but I want you to be able to recognize these if you see them on the ACS exam. They should be a clue to you that we're talking about a Suzuki reaction. So BBN or this big ugly thing here, calcylborane. Okay. For the purposes of my exam, if you just put B, Y2 or X2 or R2 or whatever, that's fine. The only reason that they use Y instead of R is because there's already a lot of R's going on the paper. Okay, and then if I'm doing a Heck reaction, so first of all, again, Heck reactions don't really take an organometallic. What are the substrates that we use in a Heck reaction that isn't the alkyl halide?
Alkene.
Yeah, so just a straight up alkene. Importantly, it has to have a vinyl hydrogen. That's what's going to be sort of substituted, is you're taking off a vinyl hydrogen and replacing it with whatever the R group from your alkyl halide is. Or not, I'm always going to say alkyl halide because it's drilled into my head. I really just mean halide because it's more broad than that. And what are my halides for the Heck reaction?
Iodine and bromine.
Yeah, you're absolutely right. So that's going to be what the actual X values are, but what are going to be the R groups that are allowed on that halide?
Aryl, vinyl, or benzyl.
Yep, aryl, vinyl, or benzyl. Okay, so now everybody take a second and look over this list and figure out what is common in all these groups. Okay, and again, sort of with the exception of this one, because it's not really an organometallic, what's shared by all these groups?
Is it an aryl and a vinyl?
Yeah, an aryl is in all of them. And vinyl is in all of them. Okay, so, the bottom line, when in doubt, aryl and vinyl, right? But it also sort of narrows it down such that this big ugly box, this big ugly list is not as intimidating as it actually looks. We don't have to bother memorizing aryl or vinyl because they're in all categories, right? So you can just focus on the differences between them to kind of help you remember these for the exam. Okay, cool. So this is kind of just like our cheat sheet of the different substrates that we can have for these organometallics. All right, so one of the ones that was not really news to us, we had learned before, were Grignard organometallics. And so we have a bunch of different substrates that we know react with Grignard. So let's just go ahead and create a little reaction wheel here. What happens with ketone? All right, and I'm being a little lazy because the second step in all of these is going to be hitting it with some sort of proton source, either acid or water. Either would work in practice. A weak acid solution is used because then it will sort of neutralize the whole thing by reacting with any remaining Grignard. All right, so let's start with the ketone. What's my new functional group that's formed?
An alcohol?
An alcohol, yeah. And then importantly, this is something that's always a really good idea to do. I know I've said it a million times, but it is an easy way to avoid making mistakes. How many carbons should be in my final product?
Wouldn't there be 5?
5, yeah. So I mean, you might even see like on the answer keys, sometimes I've gone back and like counted carbons. I'm just making sure I've done it correctly. So here, and like even going as far as to kind of color code here. So I have 2 carbons. I know that my new bond is going to be made with my carbonyl carbon. Now that's going to have an alcohol group on there. And then I have those 2, right? So just sort of color coding here. You know, the first part of the first hard part of this chapter is this: keeping track of what's allowed and what's not allowed, because there's a lot of overlap, but there's some subtle differences, all that jazz. The other thing that's really hard is anytime we're creating new carbon-carbon bonds, the molecules that we get out on the other side are really kind of intimidating. I think that that was a problem that a lot of people had with chapter 21, the aldol, or the alpha carbon chemistry chapter, is a lot of those products are really ugly, right? Like a Robinson unalation. I feel like people look at that and they just are like, I'm not going to get this. That's ridiculous looking. So taking a step back kind of helps in making sure that you're counting carbons, doing these sort of double checks to make sure. I mean, for the longest time, we were doing reactions where we were going from that to that. And now all of a sudden we got products that, you know, look like this or something, right? So there's sort of this intimidation factor that's been introduced because we're dealing with bigger, uglier molecules. But actually, if you kind of break it down step by step, it's all pretty simple. And again, the easiest thing that you can do to make sure that you haven't made a dumb mistake is to just count carbons. Okay. Epoxide. How many carbons should my product have? Let's start there.
4.
4, yep. So we got the 2 from the Grignard, 3, 4, and then an alcohol group. Okay. Again, just keeping my orange as the carbons that were part of the Grignard. And then let's actually color this carbon here. Notice that the alcohol group, right before it was this bond here that was formed. So my new bond was formed with the carbon that has the alcohol group. What are the signatures of reacting with an epoxide is, first of all, you create a terminal alcohol, but importantly, your new bond is located 2 carbons away from that alcohol functional group. CO2, what's my functional group going to be?
Carboxylic acid.
Carboxylic acid, awesome. And again, I've added just 1 carbon, right? So that's an easy mistake to make with CO2, is you sort of have it in your mind that it's going to create a carboxylic acid. Remember that you've grown your carbon backbone by exactly 1 carbon. Okay, for my ester, how many carbons is my product going to have?
Is it 5?
It's not 5. 5 would be if there was 1 addition of my Grignard, but when I have an ester, what do I have?
6?
No, so nope. You're going to have an addition of 2 of these Grignards to your reaction. So the first step is going to be like replacing this ester group. Remember, so the first step, if we were doing our reaction mechanism, we create our tetrahedral intermediate But then this in blue right here in cyan is going to act as a leaving group. So I first create a ketone, but then a ketone reacts with a Grignard, right? We saw that just up here. So it undergoes another round of addition. And so instead, I'm going to have seven carbons in my product. And again, two of them, or rather 4 carbons, come from an addition of 2 of your Grignard. All right, so first you create a ketone, but then the ketone just reacts again. So you're gonna have 2 additions.
Oh, so pretty much what happens is that there's a leaving group that goes on.
So if we just want to do the mechanism, what's going to happen is we're going to have the nucleophilic attack of the carbonyl carbon. This creates that tetrahedral intermediate. And what do we ask ourselves when we get a tetrahedral intermediate?
Is there a good leaving group?
Is there a good leaving group? In this case, there is. And so that's going to be what happens, is that this gets kicked off. And so now we have a ketone, but again, our ketone can react with a Grignard. This creates another tetrahedral intermediate. And what do we ask ourselves? Is there a good leaving group? In this case, there isn't, because they're all carbons or hydrogens would be another example of something that couldn't be a leaving group. So the only thing that we can do is hit it with the acid or water in this second step and protonate that. Okay. What about my acyl chloride? How many carbons are going to be in my product?
Four.
Not 4.
5.
Not 5. One more.
6.
6. So an acyl chloride is like literally the exact, I mean, I started out with 1 fewer. So if I went through and modified, it's exactly the exact same mechanism as an ester. I'm just replacing that leaving group now with a chlorine. So if I went through this reaction mechanism here and replaced that ester group with a chlorine, I would have the exact same mechanism. So again, I'm going to have 1, 2, 2 additions of my Grignard to this acyl chloride. Okay, so, right, both of these are carboxylic acid derivatives. With regard to a Grignard reaction, you can have them in the exact same place in your mind. You're going to have 2 additions to both. Okay, and lastly, with the nitrile, what's my functional group that I'm going to get at the end?
Is it a ketone?
It's a ketone, yeah. So, and the other easy mistake to make in these reactions are to not account for the carbon that's in the nitrile group. So that means my product should have 1, 2, 3, 4, 5 carbons. And that ketone is going to go on that carbon from the nitrile group. So this one here is what's going to get this ketone. So looking at our reaction wheel, notice that this one sort of stands out as being the only one that doesn't create a hydroxyl group, right? Most Grignard reactions that we've seen, they create alcohols, or in the case of CO2, creates actually a carboxylic acid, but it's a super similar mechanism. So we're used to seeing hydroxyl groups created. With the nitrile, the big difference is that we've actually created a ketone. Okay, and why does this ketone group not just react with the Grignard? That's kind of a hard one. Because it actually isn't created until the second step. The first thing that's created is one of these guys. What do we call those? When you got a nitrogen with a double bond to a carbon. Somebody tell me, going back to chapter, I think 20, ketones and aldehydes, nitrogen nucleophiles. Right? What happens when we take a ketone? And we react it with ammonia, we get this kind of doohickey here. What are those called?
Is it an amine?
It is. Awesome. An imine. First you form an imine, and then it isn't until this second step where you hit it with acid that nitrogen gets replaced by the oxygen. Okay, but bottom line is at the end of the day, you get a ketone when you react with a nitrile. Okay. So now if instead of a Grignard, there's some overlap here in terms of the electrophiles that we can use with the Gilman, there are some differences as well. Okay, so let's just do these quickly. Gilman with a ketone. Does a Gilman react with a ketone? So a Gilman does not react with a ketone, and it does not react with an ester. It will only react with an acyl chloride. Remember, we want to think of Gilmans as if they were weak Grignards. And unlike a Grignard, remember up here, we saw that we had 2 rounds of addition to our acyl chloride. If we were using a Gilman, we would only have 1 round of addition, which would leave us with a ketone product. And again, the Gilman can't react with the ketone, so it's not going to undergo a second round. What we did see is that Gilman can be used to sort of create fairly simple, no what, Theo? What's your question? Oh, were you answering? I get it. Yeah, so no reaction with the ketone, no reaction with a ester, only with an acyl chloride in terms of our carboxylic acid derivatives. And again, the big difference between that and a Grignard is only 1 round of addition. Okay, but again, we saw actually a new substrate in this chapter of what a Gilman can react with, which is actually quite powerful. So how would we create something like this from a Gilman? And actually, I guess we could create many of the different bonds in this compound here, but specifically creating this bond here, what 2 substrates will be used. Okay, and one of the things that sort of to get in the habit of in this chapter, once you've identified the bond that's being created, kind of sever that there and then identify your 2 halves, right? So if this is the new bond that would be being formed, that's between a vinyl, and this is also a vinyl group. So then I can go back to my cheat sheet, and I mean, here I'm telling you it's Gilman. But if we didn't know it was Gilman and I was just asking you to make this compound and create that bond, we could go back to our cheat sheet and figure out which one of these methods could be used for that. All right, turns out all of them, because like we said, vinyl falls into all those categories, but nonetheless, one of the powerful things we learned about with the Gilman, first of all, it'll preserve stereochemistry, so that's nice. So if I start out with a Z stereoisomer, it'll stay Z in my product. But really what I was going for here is that it can react with an alkyl halide.
So then I have a question.
Yeah.
Since they're both vinyl, does it matter which one you attach to which?
In this particular one, no, because either way, the stereochemistry is preserved in either half, right? So you're absolutely right. I could have also done it with that would have worked just as well.
Okay, cool.
Can you go over an example where it does matter, like which one you would have to choose?
Yeah. So actually, out of our cheat sheet of reactions here. So actually, you guys are kind of going to do this next. So we've done it for a Gilman, right? We have, like I said, any one of those reactions that we made our cheat sheet for. Again, vinyl was in all of these categories, right? So I want you guys to now create a little wheel. Cool. So we have our Gilman side. Now you're going to do a Suzuki, a still, and a heck. Give me the different reactants that we would need to create this exact same compound using these 4 methods. And yes, Andre, sort of where you're going is one of these, it does matter. And so let's go through and figure out what that is. But first I want to give everybody a second to try this on their own. All right, so we actually sort of, I mean, we could keep our alkyl halide the exact same for each, for at least the Gilman, the Suzuki, and the Still, sort of copy this same template, but let me just show you kind of how in my mind, how I do this sort of thing. I have this product here, and I know what bond's gonna be formed, right? So I'm just gonna break it at that bond, take this chunk, take this chunk. One of them is going to have to be, in the case of the Suzuki, my metallic is the boron, the borate. And then this half can be my alkyl halide. Again, Suzuki, it doesn't matter because stereochemistry is preserved for both of them. Same thing with the Still. If I just want to sort of, just to have it be a little bit different, again, kind of in my mind, I'm breaking it at this bond and I'm taking each fragment just to mix it up. We can make this one the organometallic and this one the alkyl halide. What about the Heck reaction? Actually, here, let me, I'm gonna make some room here. So this would be Suzuki. We have the Gilman. I want to take this whole thing and move it up. So I guess my point is we kind of got two options. We can either have that. And what's the other substrate for Heck? Not a halide, but Lucas.
Alkene.
Alkene. So in this case, it would be this vinyl hydrogen that's being replaced, right? That's the key. Or I have this. And that is my alkyl halide, right? These are going to be my two choices here. So everybody use the chat and I want you to vote on whether you think it's one or two. Which combination of reactants will I use? Chelsea, what do you think?
I'm not really sure. I thought you could use both.
Cool. All right. So this is the big, again, the difference here, I guess, if we're kind of simplifying things in our mind, Gilman, Suzuki, Still, they'll preserve stereochemistry for either half, for the organohalide half or the organometallic half, not organohalide, the halide half or the organometallic half, your stereochemistry will be preserved. For the Heck reaction, for those of you who voted 1, which is correct, somebody give me an explanation as to why that is.
This is just my best guess, but is it because it has a longer carbon chain? I don't know.
That could be, one of the things is you do want the smaller half to be the alkene for efficiency. But
Yeah.
even beyond that, if this was the same length, if I added another carbon over here or something, you would still have to use 1. And the difference is because when this alkene here, I drew in that 1 hydrogen. Remember, there are 3 vinyl hydrogens on this particular compound. The vinyl hydrogen, just like over here, there would be 3. The vinyl hydrogen that's going to be replaced is the least sterically hindered one. So in this particular example, it would be this. I'm gonna have to erase just to give myself some room here. So that would give me what was my desired product. If I used this combination down below, which one of these carbons is or hydrogens is going to be replaced? 1, 2, or 3?
Probably 2.
2, right? So 2 in this case is the least sterically hindered. And that would give me something like this.
While we're on
Yeah, go for it.
Heck reactions, I had a question just kind of relevant to the Heck reactions discussion. It was number F, or letter F, not number F. I think I was
okay. Let me finish this up real quick,
Okay.
and then we'll do that.
Okay.
The bottom line is that stereochem of the alkyl halide of the I'm driving myself nuts with that. Of the halide is preserved. Right here it was Z, here it was Z, here it was E, here it was E, but the stereochem of the alkene is always going to be, again, that least sterically hindered one, which in effect will make it always E. Okay, so here my least sterically hindered hydrogen was the one over on this end. Whoops, and I actually missed a carbon right there, which is why we ended up getting the E stereochemistry up here, just like I got the E stereochemistry over here. Okay, so again, just to sort of summarize, if we look at our cheat sheet here, all 3 of these top ones, the Gilman, the Still, and the Suzuki, doesn't matter which half has the stereochemistry, it will always be preserved. With the Heck, the stereochemistry is only preserved on the halide half. Okay, sorry, Andrew, you said F?
Yeah, I did.
Give me 1 second, let me find that.
I was just confused because everybody else drew iodobenzene, and I went the other way just purely because I thought it had to be a vinyl hydrogen, and so I was just confused.
Yes, okay, so this is the other thing about a Heck reaction that you have to keep kind of separate in your brain, or rather just like the little asterisks in your brain next to Heck reactions that you have to have. Let's just do a different one. Let's do. Okay, everybody take a second and give me the products of this reaction. All right, and let's avoid making any stupid mistakes. Let's first ask ourselves, how many carbons should be in my product? All right, so Andrew, I'm pretty sure your temptation is going to be to draw something like that.
That's exactly what I drew.
Yeah, okay. The exception here is because our alkene is a ring. And when that happens, your bond is actually going to jump positions. Okay, so now it's no longer located on that carbon that has the new bond. It's located next door. And this is only when your alkene is locked in a ring. Okay, now why is that? So it's kind of this ugly explanation with regard to stereochemistry. Let's bring it up real quick. Okay. And really, honestly, I'm not expecting you guys to have memorized the mechanism. I want you to know basically this cheat sheet here, where when it's a ring, the double bond is going to bounce. But just the explanation as to why is because, you know, in all of these palladium catalyzed reactions, you have both substrates that get loaded on to the palladium itself. Okay. The key here is that it's a syn addition and a syn elimination. And what happens is when I'm locked in a ring, syn meaning that the palladium has to be on the same side as the hydrogen. But when I'm locked in a ring, because I had the syn addition over here, where my R group was on the same side as the palladium, I can't eliminate that hydrogen. So it has to come from the next door neighbor, which is over here. So again, just sort of paying attention to color coding here. Right, here was the original coloring of my alkene. Things got added such that the R group was added to the red carbon, the palladium was added to the green carbon, but the only hydrogen that can be removed is over here on that blue carbon. So that's why I have that. Okay, so it would have been at the very end of this lecture video that this was discussed if you just want to review that or whatever. But again, the bottom line is when you have an alkene that's locked in a ring, because there's this syn addition followed by a syn elimination, the only hydrogen that can be removed is not one that was originally part of the double bond. It's going to come from the next door neighbor. So actually, if you sort of look at the cheat sheet for the HEC reaction here, that's this one down at the bottom, sort of illustrating that new pi bond forms one carbon away from where that R group is added. Cool?
Yeah.
Okay, things that I didn't, okay, so the other, the ones that I spent a lot of time on these reactions, because again, the whole purpose of this is to review what I think are the harder elements of a particular lecture. Real quick, we also have this Simmons-Smith, which is essentially where I'm taking this alkene, let's actually do this. And I'm adding, and I guess what I think is the hardest part for these particular reactions is just remembering what the reagents are. So CH2I2, zinc, and copper, diethyl ether. And what do these do?
This is the one where it adds the ring.
Yeah, so if I'm thinking if I'm gonna like have one line in my mind that I have memorized, it's Simmons-Smith equals cyclopropane. It's gonna take a double bond and make it into a cyclopropane, right? So a triangle, boom, boom, boom. The other thing that we have to worry about is that stereochemistry is sort of preserved. So if it's a cis double bond, it's gonna be cis. The only other thing that I'll say is when it's symmetric, if I had started out with the symmetric one, I would only have one stereoisomer that's produced because of symmetry, right? This is a meso compound. If I didn't start out with a symmetric, just be good and write them all again. If I didn't start out with a symmetric alkene, I would have, or a symmetric cis alkene, I would have to make sure to include them both just because they're no longer meso. So these are no longer the same compound. But yes, you know, if I'm flashcarding this, the reagents I need to make sure I have memorized. But really the big thing is when I'm thinking Simmons-Smith or I'm thinking these reagents, in my mind, cyclopropane is the key. Okay, and then the other one that I hadn't spent any time on, so let's just go over, is the metathesis reaction. And what are the going to be the key catalysts that I would need there? There are two dudes' names that you should have memorized for this.
Grubbs catalyst and ethene gas.
So the big ones that I think that, you know, for the sake of my exam, the ACS exam, the names that you want to have are Grubbs. That's the most common. The other one that you may see is Schrock. Okay, those are the two names that I want you to have in your mind along with metathesis. Grubbs and Schrock. I went to school with a Charles Grubbs, so that one's easier for me to remember. Okay, and so now let's just do an example. Oh, that's not what I wanted. What do I have when I take one of these terminal alkenes and hit it with a Grubbs catalyst? Give me the product there. Let's actually do a few here.
Dr. Crucipius, I have a question.
Yeah.
So I'm gonna turn on my camera to show you because I can't really articulate it.
Okay.
Just 1 second.
I mean, to answer your question simply, you do have wedges and dashes with the when you have trichloromethane and base as well. Let's see there. Yeah,
For number 2, is it correct?
that is correct. Yeah. So if you have, basically you had one bond that already had stereochemistry associated with it in the ring, and the new cyclopropane can form on either side of that.
All right, thank you.
Yeah. Okay. So first of all, how many carbons are going to be in my big product for this first reaction here? I guess just to say, ethene gas or ethylene gas is always going to be something that's produced in these. That's what's driving this reaction. How many carbons are going to be in the bigger product that's produced?
Eight.
8. Yeah, nice. So one of the sort of things to keep in mind about these reactions are you're kind of like severing this double bond in half here. So when I'm forming my new product, I'm only going to use 1/2 of that alkene, or like one side of that double bond. So in this case, oh no, there's one extra carbon there. And then unlike our other reactions, this is not a stereospecific reaction, meaning I'm always going to get every possible stereoisomer out of there. So in this case, I'll have both the E and the Z stereoisomer produced.
Will you have a major and a minor product due to like steric concerns, or?
Nope. Well, not as far as we're concerned, no. Okay. In practice, probably a little bit, but not as far as we're concerned. What about when I have two alkenes in the same molecule? What happens?
You form a ring.
You form a ring. And again, kind of the hard part is remembering that I'm cutting these bonds in half. So not every single carbon that's in the starting molecule is going to be in that ring. It's going to be these 1, 2, 3, 4, 5, 6 carbons here. Because the other two, this one and this one, are going to be in that ethene or ethylene gas. Okay, and I guess real quick, let me just show you how I would kind of think of these, because clearly I'm going to have to kink this linear molecule into a ring, right? So the first thing I'm going to do is just note that it's a 1, 2, 3, 4, 5, 6 membered ring. So I'm just going to start by drawing out my hexagon. If I want to label my carbons, 1, 2, 3, 4, 5, 6, one of these needs to be replaced with an oxygen, right? That's position 5. And then where's my new double bond going to be? Between carbons what and what?
1
1
and
and
6.
6.
1 and 6. Awesome. Right. So it's just an easy way to kind of double check to make sure that you've got your connections where they should be. All right. And then this one was from the homework, but it's a good one because it's kind of tough. 5 Grubbs catalyst, and I now pump in some ethene gas. What's going to happen? Before I had a ring closure, this is going to be
A ring opening.
a ring opening. And so everybody take a second and see if you can't tell me what my ring opening product will be. Again, this one's kind of hard because you got to keep track of who's bonded to who, where the double bond is, all that good stuff. So using this same strategy of kind of like numbering carbons is a good way just to keep track of what's what. Okay, So again, just to sort of walk you through my thought process here. Obviously, the name of the game is I need to make sure that everything that's on the right or on the left gets accounted for on the right. And unlike with the ring closures, where I was sort of deleting carbons, right? So for example, up here at the top, I was getting rid of these 2 terminal carbons, leaving me with a 6-membered ring. Now for every double bond that I cut, I'm gonna have to add 2 carbons. In this case, there's actually 2 double bonds. So I'm gonna cut here, and I'm gonna cut here. So what I'm gonna do is first, I'm gonna concern myself with accounting for these 5 carbons. Let's just start there. Number these guys, 1, 2, 3, 4, 5, okay? So this is going to be a ring opening, so I can just go ahead and do 1, 2, 3, 4, 5 carbons. Except for 1 and 5 there was originally a double bond between them. So what am I gonna need to add to carbons 1 and 5?
Double bonds.
Yeah, so I'm gonna have to include 2 new carbons on either end there, right? That's to account for the carbons that I placed when that were originally actually part of this ethene, have now sort of inserted into my double bond here. In addition, what am I going to have to do to carbon 3?
Add a double bond.
Yeah, right. So again, just like we said for carbons 1 and 5, there was originally a double bond there. And so that's also going to get one of these ethene carbons here. Now that that's done, I can account for these, and I'm just going to use sort of like a different color or here, let's do this. Use blue. And I can number them as well, just so we can keep track of what's what. So notice that off of carbon 4, on my original chunk, I have to start adding carbons. I got to add 4 of them. 1, 2, 3, 4. And then am I done?
Missing the other double bond.
Exactly. So now I have to put that other, right, wherever I had a double bond before, I have to add 2 carbons, 1 to either side. So then this accounts for, these are my 1, 2, 3, 4, and I've added that additional carbon.
If you draw it still kind of curled up in its original shape as an answer, is that wrong? Do we have to spread it out into the line?
I mean, as long as you don't have any like illegal bond geometries going on, right? Like, I guess my point being is you couldn't just do something like that.
Mm-hmm.
That's not going to cut it. But yeah, if you had kinks in there and everything like that, that's all well and good. Yeah, I mean, I totally understand what you're saying. It's sort of like making it complicated by stretching it out. But the whole point is to get into the habit of just being able to account for carbons. Because really, thinking we're on an ACS exam where this is part of a multiple choice, A, B, C, D, you want to be able to recognize it all drawn out.
Makes sense.
Cool. All right. So you guys have